Our speaker is Divyeshkumar of ARM Embedded Technologies, again from Bangalore. Divyesh is currently leading the SCIO modelling group at ARM. Prior to ARM, he worked at ST Microelectronics in IO characterization group and has been in industry for more than 8 years. His area of interest is physical IP modelling and low power flows, and has presented at different EDA forums on various topics pertaining to low power. And the topic of the talk today from Divyesh is challenges with power-aware simulation and verification methodologies. Thank you. Over to you, Divyesh.
Okay, thanks, Mike. Thanks for the introduction. So, I think my topic today, as Mike highlighted, is challenges with power simulation and verification methodology. So this is what is the agenda for today's talk. So I'll just go through the short introduction on what is this low power flow and overview of the power over simulation flow. Then there are a few topics like integrated power over Verilog model, liberty-based assertions, and UPF macro model using successive refinement, which are generally related to the end user's impact. And then as an IP vendor, how to ascertain various verifications using the library validation flow. And then I would summarize the presentation. So there's a constant push right now in the electronic products, both for energy and power efficient products, which has resulted in increased design implementation complexity. And with such complexity, it's important that we catch issues early in the cycle so that we don't lose much time in terms of fixing those and again doing the respin of those issues. So IEEE 1801, also known as UPF, allows user to define power intent, which can be used during the entire implementation flow. And using this UPF, one can perform the power over simulation right from the RTL stage. So power over simulation is one of the way to verify your dynamic power sequencing and some of the power related issues apart from static rule checks, for which there are other tools. So my focus will be on the power simulation. So this is an overview of at what all stage generally we can execute the power over simulations and what are the different views or physical IP views which get consumed. So if we see this, I think any normal simulation, it starts with an RTL and a test bench. But in a low power flow, you have to specify the power intent in Design UPF along with RTL and provide it to the simulator. So for the standard cells, generally are not involved at the RTL stage. But for the memories and IOs, you don't have the functionality which you can model it using behavioral models. So you need to use the physical IP views like Liberty and functional Verilog models for those IPs and directly instantiate, which are directly instantiated into your RTL while doing the functional simulation. So that is where you can do the power simulation at the RTL stage. Now, once your RTL and Design UPF, you feed it to the synthesis tool. For synthesis, it also needs the corresponding technology libraries, and you get a synthesized netlist. So that you can feed it to power simulation. And again, the same test bench which you have used at RTL can be used. But now, apart from IO and memory library views, your behavioral code will be synthesized into the standard cells. So your netlist will have standard cell instantiation. So you need to provide the liberties for standard cell as well as Verilog model for the standard cell. And then you again take the same netlist to the PNR and do the implementation where your power and grounds will come into the picture, and those will get translated into your netlist as well. So once the netlist which is generated post PNR, you take it to the simulation, you don't need actually the Liberty view, because Liberty captures your power intent, but now as your netlist is already having, you can use the power over Verilog itself along with the PG netlist generated by the PNR tool. So as you can see in the last step, there's no liberty involved in the running power over simulation. So these are the various stages where you can use power over simulation and various physical IP views which are involved in running the simulation. So I have some of the snapshot of just to give an introduction to the people who are not aware of. So this is in Design UPF. So in an UPF, what we have it is like you create some supply sets and define what are the different powers or supplies in that particular set, like a power ground, N will supply, P will supply, and then create a domain and then associate respective supply set with that particular power domain. Also classify your inputs and outputs with respect to your supply set, from where they are operated to, and then you can define some of the rules like power switch rule. If your any domain is switchable, then you have to define isolation for the domain crossing from switchable to always on. You have to create retention rule for retaining the values in the switchable domain. Then you have to create level shifter rules for if any signal is getting transferred from high voltage to low voltage or vice versa. And then you define what are the valid operating modes for each supply set and the power modes in terms of for each power domain, what are the different configurations when all supply sets are used together. So this is what typically we capture in the Design UPF. And then this is a sample liberty model. So this is a sort of an cell power intent you can consider. So as you can see, I have taken an example of an isolation level shifter, which is also known as enable level shifter. So you can see certain attributes like is level shifted true, that makes it that this is a level shifter cell. Then level shifter type, it's high to low and low to high, so it's a bidirectional. Then it's an input voltage range and output voltage range. So what are the ranges between which it can do the level shifting function? And then there are power pins defined and ground pins defined, and then various properties of those pins are defined, like what is the purpose of that rail, and again whether it is an pass-through rail or whether it is a routing rail. So the standard cell mean rail defines that it's an pass-through rail which will get abutted, and for each pin again you associate corresponding power and ground pin by using related power ground supply and bias pin by related bias pin. And there are attributes like level shifter data pin true, which says that this is a data pin. Then again level shifter enable pin true, that says that that pin is an enable pin. And then you define a power down function for the output pin, which says that when this particular pin will not be operational. So these are the type of low power attributes which typically resides in the liberty, which are consumed by the tool when we do the low power simulations. Then another physical IP which is involved in simulation is the Verilog. So we have discussed, seen in the flow, there are two types of Verilog, functional and power aware. So when you are giving a liberty, only functional Verilog is needed. So in functional Verilog, it's just an like an enable level shifter. This is an AND type of enable, so it's just an AND gate functionality. You don't need any power functionality here because that will be taken from the low power attributes residing in the liberty. But as we have seen post PNR, you need a power aware model. So in power aware model, apart from your input pins and output pins, you also have the PG pins, and you need to model it like how is your functionality of output impacted by signal pin as well as power pins. So it will be self-sufficient and you don't need to overlay any low power features from the liberty onto this model to realize the power of behavior. So this is the difference between functional and power Verilog model. So now I'll go into the issues of like what various issues we face at the system level power aware simulation and what are some of the proposals we have for those issues. So first one is the integrated Verilog model. So right now, as we have seen that as a physical IP vendor have to maintain two separate models, functional and power aware Verilog models, and they have to rely on simulator to infer the correct functionality from functional Verilog plus the liberty model, and that should match to the power-aware Verilog model. If that doesn't happen, then the impact is that they have to maintain the separate test benches. So one will be running at the RTL and post-synthesis stage where this overlay is happening, and then one separate one for post-PNR where actually you are just using the power-aware Verilog models. So how to get rid of this? So the proposal is to embed the power functionality in the functional Verilog itself. So by doing this, what will happen is simulator should disable the overlaying of power functionality from the Liberty onto the Verilog model if it finds that the power functionality is already present inside the Verilog model. So by this approach, a same Verilog model can be used for all types of simulations, may it be the functional simulation power with UPF or without UPF. And from an IP vendor, it's a reduction in the development as well as verification over it, because now there is no two different model. And from the customer flow impact, there is not much impact because their use model will not change. They should not see any difference in the interface they are using except some additional switches. So right now the support for power-aware simulation without UPF is still in concept phase. So currently we will be talking about the functional simulation and how it can be used, this power-aware, so that simulator doesn't overlay that information. So here is an example. So as you can see, I have taken a case here. So there's an IO ring and there's a core block. So in core block, I have two things, power management block and logic. And in the IO ring, I have a supply pad VDD, and there is an PV sense, which is a power control cell in the IO ring. And what it does is it takes some input and it takes one control signal and a supply from the power management block, and it sends both that signals, and based on that it generates RTO and SNS signals. So the signals are the power control signals in IO ring, and based on that the bidirectional pad will operate. So now in this case, if you want to simulate this type of environment in your RTL, now there is no way that you can have a correct functionality unless you have the VDDs and power pins in your Verilogs. But if that Verilog is used, your RTL doesn't have the PG pins, so you cannot simulate it. That's a problem. So that's when the need for integrated power-aware model comes. So as you can see that the model shown here doesn't have the power pins in the port list. So, but the power pins are tied internally as supply 1 and supply 0. And then model is completely power-aware. As you can see that if supply is assigned RTO, if DVD is not present, then you assign the 0 value to RTO, or else you assign the RTO reg value, and RTO reg value is generated below based on the VDD state. So if VDD is not present, then it will give not of RTO and RTN. If VDD is present, then both signals will be just in off state. So these are tied internally, and it's a complete power-aware model. The only thing is now, if it is used normally, then supplies are tied internally, so it will just filter out supply functionality and it will be a normal Verilog. But in a power-aware simulation, what simulator will do is it will just disconnect this supply 1 and supply 0 from within the model and tie it with at the top level from the UPF supplies, and then this model can be directly used as an power-aware model without supply port being instantiated in the port list. So here is the behavior of this particular cells. So you can see that this is the true table of PV sense, which is a power control cell within the IO, and this is a bidirectional cell, a true table. So as you can see that if both supplies are on, RTO and SNS are 1, 1. And if return is 0, and if VDD is off, RTO will be 1, SNS will be 0. And if DVD is off, both will be 0, 0. So same behavior, if you see in the waveform, is seen inside the waveform, that when sleep is this one DVD is 0, at that time SNS is going to 0, and if when DVD is going to 0, both RTO and SNS are going to 0. And this behavior I'm able to simulate using the integrated power or Verilog model. And Then coming to the binder, this SNS and RTO signals which are generated by PV sense are going to the binder, and in binder the functionality of pad and Y are determined by this control signal. So if both supplies are on and signal both the RTO and SNS are 1, it behaves normally. So your input will go to the pad and will be looped back to the Y. But let's say if VDD is off, then pad goes to the Z state and going to 0. And if DVD, that is an IO side supply, is off, then both gets X. So same is seen in the waveform as well. You can see that here the pad is blue, shown in the blue color, that is a Z state, whereas when DVD is going down, both are in red, that is an X state. So this way we are able to actually get the power level behavior for the normal IO cell. Then I'll go to the liberty-based assertions. So in that one, today's problem is like normal retention capability. So even basic save and restore operation could depend on complex sequencing of various control signals, and any incorrect states for the clock set or reset could result in violation of power control signal and could cause incorrect retention values. So we need to ensure that protocols are followed properly, but the concern is that synthesis tool picks the retention functionality just based on the cell classification and functionality. So if this particular issue is ignored, then cell escapes can happen and it can lead to the silicon failures. So what we are proposing is use the low power attributes defining in the liberty to infer the assertion proofs and firings. So we can instrument an SV based assertion, that is system Verilog based assertion, within the tool to check the protocol violation, and even the tool can report at what time that particular violation is happening based on that attributes which are defined in the liberty. So I'll show you an example of that one. So here is a sample liberty. So for a retention flop. So as you can see in the retention pin, there is an attributes like save action, restore condition, and restore edge. So this all things captures the restore protocol requirements. So this says that save action is when this pin goes to a high value. Restore action says that it happens when this pin goes to a 0 value, that is low. And to do a proper restore, there's a restore condition that you need to hold the clock low, and this condition should be met at the time of restore action. So restore action is not just individual, it's the combination of restore action and restore edge. So actually it's low and then trailing. So that means when it's going from low to high, that edge is the actual restore event, and at that time we need to ensure that the clock should be low. So now these attributes are already available in the liberties. So we have an simulator if reads this particular information as. So in this one, you can see that in the first stage the violation is not happening because at that time the clock is low, whereas at the second edge where the yellow line is there, there is a violation happening, and the same is reported by the tool saying that what is the actual condition. It can pretty much highlight what is the violation, that knot of clock is not maintained when retention is going from low to high. So this will help user in enforcing the requirements which are needed by the cell design. Then third one is UPF macro model using successive refinement flow. So here the problem is, I think right now there is no automated way. User need to know the boundary, interface, and power information, and then write down the connect supply net commands. And that information is found in form of PG pins inside the liberty. So and also liberty lacks support for certain attributes like feed through and floating ports, so which are just a pass through ports within the cell, or like what are the valid power mode combinations. So this power mode combination is still not supported natively by the tool. But let's go into the solution. So right now, using the UPF model, a block that can be completely implemented can be used as it is a block. That is what we call it as a macro. So any sub-block of a design or library cell used for implementation, you can term that as a macro model. So if we use the macro model, then the advantages are like we can have all the capabilities which are missing in the Liberty as of now, and supply set based mapping makes integration much more easier, unlike defining the connect supply command now. But the problem is tools are not supporting them natively, and they are in the just catching up mode. So intermediately, what we have proposed is in successive refinement eventually lead to the use of power models once they are supported. So in successive refinement, it's just allows using existing UPF commands, whereby you can update it as it is needed. So we can allow that for configuring the features which we want customer to update it, whereas the remaining things we can just model it in as an UPF file. The advantage of this approach is supported by most of the EDA tools because it's used in the hierarchical UPF flow as of now, and all UPF constructs are supported. But one limitation compared to UPF macro model is instance-based hierarchical mapping. So it's the mapping is still a challenge compared to the UPF. It's slightly complex compared to that. So this is a UPF model. So I think here I just want to highlight a cell level thing where you can define the, like within a cell, like these pins are unconnected, these pins are floating. So UPF does have a capability of providing that. And as you define in the normal UPF model, at the macro level also you can define what all supply combinations are possible. And then while integrating in the top level design, you can just load that cell level UPF and then associate the supply set, design supply set with corresponding cell level supply set. So using this approach, you should be able to get the behavior. So I have given an example here where again there is an power management cell, then there is an section of the ring in between, which is an analog, and then again on power bidirectional cell is there. So the bidirectional cell and the power control cell, which is PV sense, are operating in same voltage domain, whereas there's an analog cell sitting in between. So now what will happen if an analog power domain is down? It will corrupt the control signal unless you define those control signals as feed through and floating. So in the first waveform, if you see, Liberty doesn't provide this capability. So when analog power is down, it corrupts all the control signal and resulting in corruption of the signals in the bider. But with this particular approach, I'm able to guide the tool saying that these signals are floating or feed through, and because of that, it just doesn't corrupt those signals, resulting in that I'm able to simulate the correct behavior of the bider. So using Liberty right now, we cannot solve this problem. So that's when the successive refinement flow will help, whereby we provide separate UPF models for this one. And then the final topic is library validation flow. So I think we have discussed about all this enhancement. So, but this modeling like power down function, related power and ground attributes, if these things are not modeled properly, you can have unexpected signal corruption, or let's say some flows assumes the cells based on the cell attributes. If those attributes are not defined correctly, policy to cell mapping will not happen, and this could lead to wrong interpretation by the simulators, or even sometimes UPF standard limitation doesn't allow you to model the correct cells. So all this needs to be verified at the IP level. So to verify those things, we have proposed a library level check where you fed in the Liberty and the Verilog views, and we provide the validation UPF and low power vectors for each cell, using which there's an inbuilt infrastructure at ARM, which we are using to translate that into the design UPF containing all cell and the Testbench containing all cell, which we fed into the simulator. So this is how the UPF will look like. So we just create an always on block and put it in a particular domain, and then you create a switchable domain inside that one, and then you just define the power switches for that. So here is an power and ground switches, and then you place a cell to be tested under that switchable domain. So example is for a retention cell, and you define the control for the retention, and then you define a policy which associates that retention with that particular cell. And after that, we write a test bench using which we fed in the vectors. So part of the test bench, two things are done. One is that you do the instantiation of that cell and then assign the supplies with the values. So always on supplies are directly controlled through the test benches, and switchable supplies are controlled through the signal, which is passed on to the UPF, which will turn off the UPF control switch, and thereby we'll get the power on function. So here is an one of the restore protocol we are checking. As you can see here, that first of all, retention is going from 1 to 0, so you're going in the retain mode, and then we are doing a power off, and then we are doing a power on, and then we are doing a restore. And at all these vectors, there is an last column shows the expected value, which is compared with the simulated value. If that doesn't match, it shows that simulation is not working as expected. So that is it. So as we have seen, power over simulation is a very powerful way to check the design power requirement early in the implementation cycle, but power over simulation is still in early phase, and with increasing complexity, more checkpoints needs to be put in place. So we discussed a few of the enhancements that fixes some of the existing quality holes in the current power over simulation flow. And I think with increasing flow requirements, the library modeling complexity is also increasing. So there is a necessity to have advanced library validation flow as well to do the comprehensive verification, thereby ensure seamless power over execution flow for our partners. Thank you. And questions?
Any questions for this? Okay. Thank you, Divesh. We have one question online. You mentioned about the type that you need to increase PA-aware simulation through better checks. Can you give us an idea of some of those checks which you might want to apply?
Mike, I didn't get your initial thing. Can you repeat the question?
In your final slide, you said that for power-aware simulation, your conclusion slide, the next one.
Okay.
Early in phase with increasing complexity. Can you give us the types of more checkpoints that you need to put in place? Can you give us some examples of the types of checkpoints you mean there?
Okay, so I think one, as I told, is the feed-through and floating ports are not getting checked. So because of that, the simulation corruptions are happening. So that is one checkpoint I discussed about. And probably I think another thing which I have discussed about is the one where protocol violations are happening. So many of the dynamic protocol requirements, I think the retention one which we have captured is one of them. There may be other cell requirement, dynamic protocol requirements which right now simulators are not modeling, and unless it is explicitly modeled in the Verilog, you might not know unless it goes on the silicon. So static check doesn't catch those issues, and dynamic simulators doesn't have those capabilities. So one of the example I told was the restore protocol requirement. So now let's say simulator is not capturing that from the Liberty and it's not modeled anywhere else, then it will just pass saying that, okay, whatever you restore, your simulation environment will show that your value is getting restored. And things works fine, everything well in the simulator. But once it goes on the simulator, silicon, then probably you will see the failures. So this type of things are there which are not yet addressed by the simulators, which needs to be fixed.
Okay, thank you, Divesh. I think that's the final question, so thank you for your talk.